Okay, let's start with lecture 7. Today we're going to talk about exceptions and interrupts. First, a couple of announcements. Another note, if you start using pointers in C, there is a nice little way of how you can actually add to the pointer without having to know the size of your pointers that you're pointing at. If you have an integer pointer, like for example reg over here, if you set this register to value 0, for example, and if you increment this register by 1, this will not point to ID number 1, but it will actually point to 4. So it will automatically add the amount of the type of the size on here to this register pointer. Not by 1 byte, but in this case by 4 bytes. Okay? Another good way of having pointers and addressing arrays in it, of course, is if you have the index in here. So any type of register that you have defined like this, if you index it like this, you actually don't change the register value itself, but it will operate on the pointer plus 4 in this particular case, because we have a UN32, and set that particular value to 0. Any questions on this? Okay. A couple more announcements. We talked about the grad students' presentations. All the grad students will have to do a presentation. What's the presentation about? Well, think about an embedded system that you want to present to the class. So you should talk about what's the system architecture of this particular embedded system, where is it used, how does it work, how can I program it. Think about the audience too. So what would your peers be interested in this system, right? So for example, if you want to present the Cortex A9, show them a little bit of what kind of applications the Cortex A9 is used in. Or you can, for example, choose the Cortex R9, which is the real-time ARM Cortex course. Or you could present on the 64-bit architectures of the new ARMs. You could also just choose a completely different microcontroller architecture and present what are the advantages of these microcontroller architectures. You can present on embedded systems themselves. So for example, the Kinect. You could present how does the Kinect really work and go and dig deep into what is the neat thing about a Kinect, what's inside the Kinect, how does it tick, how does it work, and how do they make the magic of getting the 3D models out of you. You can present about quadcopters, imagers, radios, flash architectures. FRAM, for example, is a new RAM architecture. Describe what it is. You can use MRAM is also another one that might be interesting to look at, etc., etc. So if you're a grad student, sign up for a slot and start thinking what embedded systems you want to present, and then talk to me, preferably during the office hour or by email, and I can let you know if this makes sense, what you want to present, and what I would expect from you presenting this particular architecture. Okay, today we talk about interrupts. And the Merriam-Webster defines an interrupt as to break the uniformity or continuity of. And that's really all an interrupt is. An interrupt tells the microcontroller or the core that's calculating and executing your program to stop its calculations and do something else. Very simple, right? Now, devil sits in the detail. How do we make this actually work, right? Questions are, how and where does the interrupt come from? How does this interrupt go into the core itself? How do we save state, right? If you're calculating something and all of a sudden you tell it to stop wherever you are in your code within any kind of assembly instruction, within any two assembly instruction, the core can be interrupted. How do you save state, right? Like you have state on your stack, you have variables, registers. How do you save that? How can we ignore interrupts? Like sometimes we really don't care if a certain interrupt comes in, so how can we just ignore these interrupts? How can we prioritize interrupts? Sometimes if two interrupts come almost exactly at the same time, you want to give one of them preference to the other. And how can we share interrupts? Because at the end, you don't have that many lines into your core, not that many interrupt capabilities, so sometimes you have a lot more events that you're actually interested in, but only very few interrupt lines, so how can you share one of these interrupt lines? And this is what we are talking about today in this lecture. So two key questions that we really have to answer is, when you do I/O operations, there are two ways of dealing with them, right? You can either, what you maybe have done before, you just busy loop on the register and wait until a bit is flipping to 1, and then you know, okay, now it happens and you can keep going. Or the other way is, and that that system is called polling. Or the other way of doing it, which is actually a nicer way, you do some execution, you are calculating something, and then all of a sudden your system gets interrupted with an interrupt, tells you, hey, you should execute something else right now, and you can go back to your stuff later on. So one of them is polling, a busy loop, where your system is busy just checking that one status. With interrupts, you can actually do other calculations on the background and just wait for events to happen, and you treat them as they come. Interrupts. They're also known exceptions or traps, and usually they're handled by what's called an interrupt handler or interrupt service routine, ISR. You might have heard that before. And really, interrupts or interrupt handlers are nothing else than a glorified function handler or procedure call. So what you do is you register a specific function as an interrupt handler, and when your interrupt happens, all that happens is your code stops executing whatever it does, executes that particular function that you defined as your handler, and once the handler is done, it will jump back to where it was before. Now, again, the devil sits in the details. How do you do that, right? How can you jump back to the same execution when you get interrupted all of a sudden? How are you making sure that the state is actually the same as when you entered into your interrupt handler and when you come out and go back to your function? You have to make sure that everything is the same, because else your code will just corrupt and bad stuff will happen. There are two different types of interrupts. Those that are caused by instructions. These are usually called traps or exceptions. So for example, if you do a divide by 0, you will get a trap or an exception because it's a function itself that happened. Or you can sometimes have illegal or unimplemented instructions. Yes?
So how do they implement the debugger? Because I was seeing a lot of sig traps when we were, is that?
There are some interrupts are for the debugger itself. And the debugger is actually a unit that sits outside of the core and has hooks into the core to stop it and do stuff. And yes, there is also a debug interrupt. So you can register a function for a debug interrupt, and then the function will be executed before something else happens. But usually the debugger just stops the core, and then you can go and probe the different registers and stuff like that. The second type is instructions that are caused by external events. So these are external. These are not functions that actually make these interrupts happen, but they are, for example, an external device, peripheral, the reset button, timers that expires. Sometimes you have power failure, so if your power dips underneath a certain threshold, you can get an interrupt, so you can do some emergency things. Or particular system errors that just happen on the bus system, for example. You can also get interrupts from them. And these are usually called interrupts or external interrupts. So two different types, traps, exceptions, and interrupts. Interrupts usually from external, traps, exceptions from your code that you're writing. So how does it work? Well, there's something out there that tells the processor to stop its core right where it is. The core then transfers and control to the core then transfers into the code that has to be executed, so the function that you registered. And the said code then executes, returns, and the old program gets executed at the next function that has to be executed. Anybody know why this could be hard? What are the things that you have to do in a function? What does the ABI define? Sorry?
Pushing on the register.
All the registers?
That you want to change.
The ones you want to change? Which one?
The callies hit registers.
Yes. So that's register
0 through 4.
5 through 10, or yeah. How do you... Good. So we have to save registers. What about register 0 through 4?
They're volatile.
They are?
They're volatile. Like you can't guarantee that the values that you save.
Exactly. In a function at least. Yes?
You have to save them because an interrupt can happen anywhere.
Exactly.
R0 interrupt R0, you have that reserved.
So in an interrupt handler, you have to take care of that, right? Because now you interrupt any kind of code wherever. You don't know. You might do operation on R0. It's not like you're calling a function where R0 through R4 are parameters. So that's why they are scratch registers in a function call. In an interrupt handler, you actually have to save them. What else do we have? Yes?
You have to update the program counter to the new code.
Exactly. Right? The program counter is now pointing to the new code. So how do you get back to where you came from?
You have to save the address.
Sorry?
You have to save the address, current address.
You have to save the address, exactly. So somehow you have to save the address of where you came from. Which register is usually used for that? Link register, right. So let's put that into the link register. Now what? What just happened?
You no longer would arbitrary.
Well, you overwrote something in the link register. What happened if you were in the function where the link register was used for you to go back to where you came from the function? Now you're in the interrupt handler, that link register got overwritten. So from that function, you will never find back. So link register also has to be saved somewhere. What about the stack? I've also made sure that the stack is exactly the same when you leave the handler as it was before. You can use it, but it's dangerous. Okay, so let's look at this in details, right? So these are a couple of things. How do we figure out where to branch to? So how do we actually find the actual interrupt handler? And then how do we return from it? What about pipelines? Modern microcontrollers, computers, they have huge pipelines, right? What do we do with the whole pipeline if you have an interrupt? What if some of the functions inside that got rearranged and then that function actually starts to have an interrupt and functions that are later on in the pipeline already happen? So all kinds of complications. Yes?
Probably if it hasn't been back, then it never happened. The whole pipeline is flushed.
The pipeline is flushed, yes, but that's very expensive, right? If you have to flush the pipeline. So maybe there are tricks to deal with that. What if we are in a critical section? What if you're controlling a nuke right now and you really don't want to be interrupted, right, by doing something? Ignore it, exactly. And there are ways of doing that. So let's answer the question where. If you know what caused the interrupt, then you can also jump to something that you registered for that. Right? Makes pretty easy sense. Now, luckily, every interrupt has a number. It's the interrupt number. And the ARM Cortex is actually defining a branch table. So it's a huge table in memory, which has just function pointers inside of it. So there is a peripheral out there or something out there that if a certain interrupt happens, for example, interrupt number 1, it will go in that table, fetch the pointer to the function in position number 1, and it will jump to that particular instruction. Very easy. That's done. So then how do we get back? Well, some of the problems that we had, we could put stuff onto the stack, but that's kind of scary, right? Because if you touch it, you're not entirely sure what happened to the stack before. So you really have to be careful. The problem is also if you use the stack, what can happen is what's called a page fault. So now in your interrupt handler, you actually generated an interrupt, and that could be a deadly busy loop that goes from interrupt handler to interrupt handler to interrupt handler to interrupt handler, and then you're dead. So the thing is that fortunately there's a dedicated register that seems to be a very good space for doing these kind of things, right? And we will look into that in detail. These are a couple of other problems, right? As I said, modern processors have 50 plus instructions that happen in the pipeline, difficult to do and deal with if an interrupt comes. Fortunately, the Cortex M3 only has a pipeline of 3 stages, so there are not that many instructions that actually are happening. And if I'm not mistaken, in the Cortex M3, the pipeline just gets flushed. But in more complicated architectures, that's not the case. All right, nesting interrupts can happen too. So you can be actually in an interrupt routine, and a new interrupt happens. And then you have to decide, do I want to handle that interrupt immediately now? Or do I want to wait until I'm done with my interrupt handler and then execute that second one before I go back to my original code? Yes?
Last slide, what do you mean by drain the pipeline?
Drain the pipeline would be flushing it. You just clear everything and start from new. Right.
So then
No, sorry, all the way around. You stop executing, drain the pipeline until the whole pipeline is empty.
okay.
But then the problem becomes, what if one of these instructions inside the pipeline causes now an interrupt? Right? So you had an interrupt, you drain the pipeline, so that means you don't load anything new into the pipeline. But within the draining itself, there could be another function that interrupts. So you have to deal with multiple interrupts inside the drain. As I said before, you could just flush the whole thing and just empty it out and say nothing of this happened, but that impacts latencies. Make sense? So draining it means you let it run until the end. Flushing means you just pump the whole work, but then you did work that is now just gone. So, but it's easier to handle. Okay, nested interrupts, just handle it. You can ignore it, or you could prioritize. So sometimes you can decide which ones do you want to take and interrupt. Other times you can say that they have to wait, or just completely ignore them at all. Critical sections are also very important, and sometimes you have to have critical sections. So there has to be some sort and some way how you can tell the system right now, please ignore everything else. I don't care, just wait until I tell you to give me all the different interrupts that should come in. In addition to that, you can use prioritization that we had just before, where we say once I re-enable interrupts and there were multiple interrupts that happen, they should be told to me in a certain order so I can execute them in an order, not maybe how they arrived, but on how I prioritize them. Okay, we already know one interrupt, and that's the reset interrupt. On reset, what does exactly happen? Who remembers? I mean, it's written all up there. But we power up, we look if all the power is good, and once the power is good, what happens? It's the last line here. We read the stack pointer from address 0, and then we jump to first instruction written at address 4, right? This is nothing else than a reset interrupt. You can imagine when your system comes up, what happens is a reset interrupt. So we have a function handler actually stored at this address 4, and the system goes and gets that reset and jumps there.
Now this is what the CPU does in reset. All the peripherals have their own stuff too. Is there like a reset line that gets asserted on all of those?
Not necessarily. I mean, on a power-up, there might be.
Well, yeah, because you can turn the peripherals.
Mm-hmm.
Okay.
But I'm not entirely sure. Sometimes peripherals come up in whatever state, and then you have to actually reset them manually on the reset line. Okay, so this is the first interrupt that you actually already saw. You just didn't notice that this is an interrupt, right? It's a function pointer to the reset handler. Whenever a reset happens, or the reset interrupt happens, it will go read the address on 4, and will jump there and actually start executing. Now the SmartFusion that you're using has a lot of different interrupt sources. It has all of these, plus a whole bunch more that down here are not shown. All of these plus 54 more from the analog compute engine. That's a lot of interrupt handlers, right? All of them are actually defined in what's called the reset interrupt vector. If you look in your code, and if you actually find the file that's called startup A2F xxxm3.s, it's an assembly file where the interrupt vector is defined. So it's defined as a list memory eStack, it's the stack pointer, reset handler, handler for the reset interrupt, NMI handler, hard fault handler, memory management, bus fault, usage fault, etc., etc. And this list goes on and on and on with definitions of labels to functions that implement these particular interrupt handlers. So far, so good?
Why do you have zeros?
Sorry?
Why do you have zeros?
They're not implemented. So these interrupts. So if you actually look at it, we have the usage fault handler. The next handler is, they're actually up here. They're not in there. We can look at it later, and which particular interrupt that is, but that one is just not defined. Can either not happen, or it's not defined in this particular case. Yes?
What is the dot word?
Dot word means that this link should be a 4-byte address. And then these things are defined as labels later on somewhere in your assembly code. Or could actually be functions in C. We will look at that later on. But so for now, what happens is an interrupt comes in, the interrupt has a certain number, and then some magic element that we'll talk about will come in here, read the jump address out from here, put this into the program counter, and the execution will continue on that position. Plus there's some other magic that will happen too, to take care of a lot of things for you. Okay, so let's go all the way down in the stack and actually look at what an interrupt really is. An interrupt is really nothing else than a signal that's a bit that goes up and goes back down again. Actually, no, it's just a signal that goes up and stays high. As soon as this particular signal, so in this case, for example, if it's a reset vector, this would be interrupt number 1, bit number 1 that comes in here into your unit. As soon as this goes up, what will happen is in a second bit, an interrupt pending status will go high. Your processor will be interrupted. It will switch from thread mode into handler mode. Inside the handler, you set the pending status low. Sometimes, in this particular case, for example, the hardware itself cleared its interrupt line. Doesn't always happen. Sometimes your software here has to actually go and clear that interrupt too. And then, once the handler is done, it will go back down into thread mode. So you have an interrupt line. As soon as this goes high, interrupt pending bit will be set. Your processor will be interrupted. It switches. You clear the pending status bit. Questions? Okay. Let's look what else can happen. This is also a possibility. For example, let's assume you ignore all interrupts. So your processor will not be interrupted, but what you can do is, an interrupt happens, your pending bit will still be set. But in your code, you can now go and clear that pending bit itself. So your processor actually never went into handler mode. It never jumped to the interrupt handler itself. You actually processed this particular interrupt inside your regular software. A little bit more complicated. We have an interrupt request that happens. The pending bit will be set. We go from thread mode into handler mode. And the interrupt has to be cleared in this particular case by software. As I said before, sometimes the hardware takes care of the interrupt and it's just going high and back low again. So the status bit will be set and that will indicate if an interrupt happened. Sometimes the software has to go and talk to the peripheral and tell it, hey, turn off your interrupt line. And then you also turn off the status line. And then you can keep going. And at the end, you go back down. Now we make this a little bit more complicated. There is another status bit where you have interrupt active status. So as soon as the microcontroller goes from thread mode into handler mode, the interrupt active status bit for this particular interrupt will go to 1. Once you go back out of this particular handler, the bit will be set back to 0. Any intuitions of why you would have like an active status bit?
In case someone's trying to interrupt you again, it's busy.
Exactly. Or if you have multiple interrupts that actually preempt each other, you can go and check if somebody else is active too, or if you are the only interrupt handler that's actually active right now. So you can check if you preempted somebody else or not. Yes?
Doesn't that signal completely indicate processor mode?
Not exactly. Because it does it for this particular interrupt. But you have multiple of these signals. So for example, you have one signal for interrupt 1, another one for interrupt 2, for 3, for 4. So if, for example, 3 and 4 are high, it will tell you that you actually have 2 handlers that are running. One of them preempted the other one. Make sense? So this active status bit will tell if you're in the interrupt handler, you can go and look if somebody else, another interrupt happened too, and you started executing it or handling it, basically. Okay, little quiz. What happens in this particular case? What do you think will happen? You have an interrupt happens, interrupt pending status bit will be set. We go into handler mode, clear the pending bit, but this is not being cleared yet. What happens if we execute the handler mode? Okay. Yes. What will happen?
Do we execute it the same interrupt handler twice?
Who thinks we execute the same interrupt handler again? Okay.
Is that you voting that you?
No, I'm not voting.
Oh, okay.
I'm just saying, show hands. Who thinks this line would just stay high, this line goes low, and we go back into threat mode? Okay. Well, the first ones were right. What will actually happen is, as soon as you get out of the active mode and out of the interrupt handler, because the interrupt line is still high, status bit will be set again, and you go right back into your interrupt handler. So you have to make sure that this interrupt gets cleared somehow. Either the peripheral does it by itself, or you have to go and tell it to shut up and turn off that interrupt so that you don't get interrupted again. Sometimes you want this kind of behavior, but usually you don't. Yes?
So the interrupt pending status is saying there's an interrupt that's occurred and we're waiting to handle it.
Correct.
And it goes low when it's begins. When the handler
Let's
goes up.
look at the next example, and it probably gets clear. What happens in this case? Right? In this case, the hardware starts toggling and gives you a lot of interrupts. In this case, 3 interrupts. What happens to the pending bit? What will happen to the interrupt active status? And what will happen to the processor? Get in teams of 2, quickly discuss this, think what happens, maybe write it down on a note. Okay, how many teams think that we will get all 3 interrupts and execute our handler 3 times? Show hand. Nobody. That's good. So how many think that we will lose some of the interrupts? Almost everybody, that's correct. Yeah, what will happen is the following. These interrupts will happen. The status bit will be set because of the first one. But these we will just lose. We won't know that they happen. Once the interrupt, the processor switches from threat mode into handler mode, interrupt will be active, this will be cleared. This one is already low from the hardware itself, so we lost 2 of the interrupts. Yes?
What if the software manages to pull down the interrupt pending status and then another interrupt?
It will be set. It will get set.
Well, I understand what he's saying. So we're
Okay,
assuming
wait.
that these pulses are shorter than our interrupt servicing time.
Yes.
Okay. That's the assumption.
This is exactly the problem you're asking for, right? So what happens? Interrupt request happened. Pending bit will get set. We go into active mode. In the handler, we clear the interrupt. And then we start processing and doing something for this particular handler. And then this pulses again. But we're still in interrupt handler mode. What will happen to this one here? The pending bit. It will go high. Right? Pending will go high. We go out, but because we're out and the pending is high, we will go right back into our handler. So the NVIC, or the Nested Vector Interrupt Controller, is part of the Cortex-M3. ARM defines that one. It's the interrupt controller on every Cortex-M3. It will always sit on this memory location, no matter who the manufacturer of your Cortex-M3 chip is. So the NVIC is always there. And it's really nice because ARM defined 15 internal interrupt sources. So these 15 interrupts will always be the same, and then it has an optional up to 240 external interrupts. That's where stuff becomes vendor specific. So these 15 interrupts will always be the exact same ones, and the other 240 can be optional. Some of them have only 30, others have all 240 sources. For example, the SmartFusion is one of them. The microcontroller that has a lot of interrupt sources, others don't have that many. Like smaller microcontrollers usually only have like 40 maybe a little bit more. So not that many other sources themselves. The NVIC is used to control, enable, disable. It has all the pending status bits inside defined. It has the enable and disables of interrupts inside and a couple of other configuration registers that we will look at right now. So for example, we have the interrupt set enable and clear enable lines. They are going from address E00, E100 to 101C, and then another set at 180 to 199C. Why do we have two of them? Why do we have a register for set and the register for clear? Remember I gave you an example over here before. Why do you think this is important? So you have a register where if you set one of the bits to 1, the interrupts will be enabled. And we have a second register where we have to set the bit to 1 to disable the interrupt again. Yes? Sorry? Yes. With this way, it's very easy to enable or disable just one interrupt, right? Without having to go read out which interrupts are actually enabled right now, doing a mask on it, and then write it back. This way, you just set one of the bits to 1, bam, it gets enabled. And only that particular interrupt, the others will be left alone. And if you read the register, you will actually see which ones are all enabled. Same for the clear. You can write into the clear and just disable that one particular interrupt that you don't want to listen to anymore. And if you read the clear, you will actually see which ones are enabled and which ones are disabled. A similar one for set pending and clear pending. So you can actually in software set an interrupt to pending if you want to. Most of the time this is the interrupt, the NVIC, that sets them to pending, but you can, if you want to, you can write into the set pending bit and the interrupt will get pended. But the more important one is the clear pending. That's the one that you will use. So in your interrupt handler, you have to write into this register at the right location to clear the pending interrupt, or else you will be called again in your interrupt handler. If, for example, if you have an interrupt handler that's set for, let's say, interrupt 1, right? So that handler will get executed, and that handler then has to write a 1 into this address at bit number 1.
To clear it, to say that it's,
To clear it.
it's not pending where you were handling it right now.
Exactly.
My question is, what resets bit 1 in your example
Yeah.
in set pending? Because right now, it's got a 1 in it.
So the set pending usually happens automatically. When an interrupt happens,
Okay.
the NVIC will set the set pending bit.
And who sets it back to 0?
You, in your code,
When do we do that?
in the interrupt handler.
Okay, just right as we handle it, we say set.
Exactly. So one of the first instructions you do in your interrupt handler is clear the pending bit.
Otherwise, it'll just stay high and we'll just keep
Exactly.
it on.
It can either be the very first one. Sometimes you want it to be the last thing you do.
Okay.
Because remember what we just saw before? If the interrupt happens again during your interrupt handler, the pending bit will be set high again. So if you clear the pending in your interrupt at the very beginning, and you then do a long execution, and your interrupt happens again, the pending bit will be set again. So as soon as you go out, you will go back in because you cleared it in the beginning. Sometimes you don't care, so you want to clear the pending bit at the end of your handler. That way you will ignore whatever interrupt happened during your interrupt handler. Yes?
Okay, so set pending gets set.
Yes.
You execute your ISR. You set a clear pending bit.
Yes.
How does set pending go back to 0? So that we don't go back into it.
It's logic. It's linked behind it.
Okay,
So yes, you do have two memory locations, but behind it sits the same logic. It's just a nicer way of handling setting and setting it to 1 or to 0, basically.
So the logic takes into account that we set a 1
Exactly.
clear pending,
Yes.
and it sets that back to 0.
Correct.
Okay, that was
So there's basically, you can imagine there's one register behind it, right? If you read any of these two, you will get that register out, that memory location. If you write a 1 into one of them, then only the ones will get set in that particular register, into the set pending. If you write 1s into the clear pending, it will set those registers to 0. The 0s are just always ignored. So when you read it out again, it doesn't matter if you read this one or this one, you will get the same value back out. Yes?
What is the, it says interrupt 0 and then parentheses exception 16. What is that?
We will get to it in a second. It's the mapping between the interrupt numbers and what they call the exception number. Because we have 15 that are actually above this. These are special purpose interrupts, like the 15 interrupts that ARM defines, that are predefined. These are actually exceptions 0 through 15. And then what starts after that is the 240 other interrupts, which are called exceptions 16 through whatever else. And they have slightly different registers to use. Yes?
What the benefit are included is there is one or six.
the benefit is, assume you have just one register, right, where you want to write zeros or ones in it. In order to just flip one of the bits, you first have to read it out, do the math on the register, like on a core register, and then write it back, right? Because else you do not want to just set other bits to zero that you're not responsible for, right? So you have to do a read and then a write back. Having two registers allows you to just write into it because you know which bit you want to certainly set to 0 or to 1 right now without caring of what the other registers do. That's the big advantage. Okay. Another register is the active status register. This will tell you if an interrupt handler for a certain exception is active right now or not. Now, one of the things that you can see here is the type is an R. That means this is a read-only register. The NVIC will control this register, but you can only read from it. You can't write. If you write into it, nothing will happen whatsoever. You can't just set an interrupt to active using software. Different from these registers, which are all read-write registers. So you can read and write from them. Okay. So what happens if you have multiple interrupts that happen at the same time? So we will see that all the pending bits will get put high. Now, in what order are we executing them? Right? It takes a little bit amount of time for the core to get out of interrupt and into the service routines. And then the NVIC has to decide which interrupts to handle before others. That's where interrupt priorities come into hand. So you can actually define which interrupts have what priority. And the NVIC is a little bit complicated in how you can do it because it has 3 fixed priorities that are highest priorities. They're not counted at all. So that's priority -3, -2, and -1. And then you have up to 256 programmable priorities. So you can have up to 256 different priorities for your interrupts themselves. Now, vendors don't have to implement all of these 256 priorities. With these 256, we can have up to 128 preemption levels. We will talk about it in a second. And what happens is, if not all of them are implemented, some of the lower bits are just read as 0. They're ignored. Right? So in this particular case, if you have the 3 highest ones and all the lowest ones are set to 0, the different priorities we can have are 0, 8, 16, so 1, 0, etc., etc. 1, 8, 2, 0, 2, 8. So these are the different priorities that you can then set. Of course, higher priority levels can preempt lower priority ones. That means that if you are in an interrupt handler of a lower priority interrupt and the higher priority comes in, it will actually jump to that interrupt handler, execute that one, and when it comes back, it goes and continues at the other interrupt handler, and then from there, it goes to the last one and back into thread mode. Yes?
How many interrupts can recursively execute at the same time?
Depends on your stack. And we will look into that in a second. Maybe not actually in this lecture, it might be in the next lecture themselves. There is a reason for it. So to just take it away a little bit, the NVIC takes care of parts of it and actually puts some of the registers onto the stack automatically for you. So if you have interrupt handler, 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 the stack will actually go down and you can smash the stack. So you have to, the programmer has to make sure that this can't happen with the different priority levels. So he has to assure that the stack is big enough to handle all preemptive threats that could happen. Make sense? It is a lot, but yeah, we will see. We will talk about it in details. Yes?
So the 3 fixed highest priority handlers, what happens when you get 3 of those at the same time?
On the same priority?
Yeah.
They get executed after each other. So if you have an interrupt and then another interrupt comes with the same priority, it will just wait until the handler executes, the handler finishes, and then it goes and executes the next handler of the other interrupt, of the same priority.
But what order does it do it? They're all on the same priority and they all get there at the same time.
Interrupt number.
Okay.
So lowest first, if I'm not mistaken. So that it will come in a second. So priorities can subdivide into priority groups. So you can actually have multiple different groups of different priority levels. We will look at that in details in a second. So where do you set this? Well, interrupt priority levels, there is a big register event again. So it goes from 400 to 4EF. And each one of these registers is the priority level for one of the interrupt lines. So for example, at E400, you have an 8-bit number that's the priority level of the external interrupt 0. 401, so 1 byte higher, it's for interrupt number 1. For 41F, for example, it's for interrupt 31, and etc., etc. So you have 1 byte per interrupt where you can configure its priority level. How does it work with the priority and the priority sub-priority? It's all complicated. Once you understand it, it's really not that hard. It's just a lot of priority, sorry. So what happens is you have a field that's called the priority group. So when you set priority group to 0, the preemption priority will be bit 7 to 1, and the sub-priority will be bit 0. What it means comes in a second. Priority group 1 means that preemption priority is bit 7 to 2, and bit 1 to 0 is the sub-priority field. All of this is stored in this address here. So in here you have the priority group bits in here. You write into these bits of this particular, at this address, that will set your priority grouping for all the different interrupts. Okay? Now comes the important exercise. What happens with these differences in preemption levels and sub-priorities? So only interrupts from different preemption levels can preempt each other, while if they have the same preemption level, even if they have different sub-priority levels, they cannot preempt each other. Make sense? So if they have different levels here, they can preempt each other. So basically an interrupt will interrupt another interrupt, and the handler will jump to a different handler and then back to the handler before it goes out. If they have the same preemption level but different sub-priorities, nothing happens. The interrupt handler will finish execution, and as soon as it's done, the next interrupt will come in line. Okay? So what happens? Let's assume we have the 2 highest bits are preemption, and the rest of the bits are sub-priority levels. These are all the different priority levels. So we can get 00, 40, 80, C0 as the preemption levels, right? These are the top 4 bits, with the sub-priorities going from 0 to 38, and down here from C0 to F8. Can anybody tell me why we have this whole complicated structure? Yeah?
An RTOS
An RTOS.
would take advantage of this.
Could I take advantage of it? How? For what?
Oh, just to different tasks would have different priorities that could preempt other ones or not be preempted.
And you can change it over time, right? Sometimes you set it up this way, and then all the ones that are in this priority level can't preempt each other. But sometimes in certain cases, you can change this preemption level, and then all of a sudden, the sub-priority, the interrupts can actually preempt each other again. It's rarely used. I have never used it myself, but the functionality is there, so you need to know on how to use it and what to do with it. What I usually do is I have everybody at the same level, except a certain few ones that get a higher level than others. I rarely use preemption in my interrupts. But then I rarely do something real-time OSs, so yeah. But the functionality is there, so you might have to take advantage of it at some point. It's a very dynamic system, very liberal. You can do a lot of different things with it. Okay. One more thing. The one very important thing that you want to do. So imagine you want to turn off all interrupts. Will you go through a big list of enable and clear interrupts and actually set all of them to 0, but remember them somewhere in memory, because as soon as you are done, you want to write all of them and re-enable all of them? No, that's really not what you want to do. So there is a special register called the PRIMASK. And if you write into the PRIMASK a 1, what will happen is it will ignore all interrupts that have a lower priority than 1. So if you write 2 into PRIMASK, it will disable all interrupts with priority level lower than 2. higher than 2. With 3, anything higher than 3, 4, etc., etc. So if you write 1 in there, almost everything is disabled except interrupts 0, -1, -2, and -3. These are these like special ones. You also have the fault mask. If you write a 1 in there, what will happen is interrupt 0 will also be disabled. And this is the hard fault interrupt. Usually you really don't want to do that because a hard fault really means something really bad happened on your system. Like you either had an instruction that was wrong or something really bad. But occasionally you want to do that and you can. Yes?
Does that mask the reset?
No. These are, reset has priority -3. So you cannot mask it. And there is also an NMI interrupt, which is the non-maskable interrupt, which has ID, I think, -1. And there's another one which has ID -2. We will look at them in a second, the whole list. So unfortunately, you can't directly write into that PRIMASK register. You actually have to use a special assembly function that's called MSR. So what you do is you move 1 into a register, and then you move that register into the PRIMASK with MSR. What you will see is there is no C equivalent for this function. So this will be some inline assembly that's actually usually happening in some hash define. They have a macro that they define for MSR where you operate on the register itself. But there is no direct C translation for this and writing into it. Okay. So what exactly is an interrupt handler? We talked about it a lot now, right? We know it gets fetched, the address of the interrupt handler gets fetched from the interrupt vector. So we have to somehow register it on there. To be more specific, what we do is, in the NVIC, it starts at address 0, which is the stack pointer initially. And then it keeps going exception 1, 2, 3, 4, 5, 6 to as many handlers that we have defined. Address 4 is the magic one for the reset vector. At 8, we have the NMI handler, which stands for non-maskable interrupt handler. So that's an interrupt that you can't mask. If that happens, it happens. And then here comes the hard fault handler, is at address C, which is at priority 0, I think. So if something goes really bad, and if you debug your system, and you halt your system because nothing happens anymore, and you find yourself in the hard fault handler, you did something really bad. So either it can be a stack that's got misaligned, you execute a function that doesn't exist, or you try and jump and switch your Cortex M3 into ARM mode, which does not exist on there, so it'll throw you a hard fault. Sometimes really difficult, because all you get is a hard fault, and you're like, oh dear, now what? So you have to sometimes very systematically step through your code until it jumps into the hard fault, and then you know which instruction was actually executing the hard fault itself. Okay. In C, it's really easy to do and manage these hard fault handlers. What we have is in this A to F startup file, we have a .global definition of a TP-NVF vector, so that's a label. It's defined as this .word stack, and the linker script in here makes sure that this interrupt vector, ISR vector down here, gets written at address 0. So at address 0, we have this list of labels or pointers into your code. Next, we have in the .s definitions like this. We have .global reset handler, type is a function. We have a reset handler here, and what it will do is it will start executing your assembly code, initializing your system. That one is all written in assembly. We have other ones that are written like this, where, for example, we have the NMI handler. It's also a function. It's a label with an infinite loop. So whenever the NMI happens, it will just get stuck in this line, and you can stop your debugging system, and you will find yourself in this line. The key here is that it's defined as weak. A weak definition means that use this handler function here unless you find another one somewhere else. So what does it mean? Well, Microsema was nice enough to provide you all the different interrupt handlers, because sometimes it happens that you define an interrupt but forgot to name the handler function correctly, or who knows what. You enable an interrupt but you didn't write a handler for it. So if an interrupt happens in your system, you will get stuck somewhere in this code. And you ask yourself, oh, what happened? So you can stop your system and you will know what interrupt happened and that somehow something is wrong with your interrupt handler that you tried to set up. So they define all the different interrupt handlers as weak for you. And if you want to overwrite them, you can do it like this in C. It's fairly easy. You just do underscore underscore attribute, interrupt, void, for example, timer1 underscore IRQ handler. And that will define your interrupt handler, in this case, for a timer unit. What you can see, first thing we do, we actually disable the interrupt. We clear the interrupt, in this case, in the peripheral. So we tell the hardware to turn off its interrupt line. And then later on, we clear the pending bit in the NVIC. This is a very typical sequence. The necessity of this one here is not always there. If the interrupt peripheral is just generating a pulse, then you don't have to go and clear it in the peripheral. In this case, the timer unit wants it to be cleared by software. So that's oftentimes you have to go into the documentation and actually read about it itself. The other couple of things that you have to do in your main function in this case, you want to enable the interrupt, of course. So this function here will tell the NVIC to set the enable bit in the right register. We then, actually no, the other way around. This one will enable the interrupt in the peripheral. This one here will enable the interrupt on the NVIC. And then, in this case, we just busy loop and wait until we get an interrupt, and then we will execute this one here. You oftentimes have to enable an interrupt in the peripheral, enable it in the NVIC, and then in the interrupt routine, you usually have to clear it in the peripheral and clear it in the NVIC itself. There's usually even more stuff that you have to do. You also have to turn the clock on to the peripheral itself. So we will talk about peripherals soon, don't worry. But usually, you have a clock signal that you can control to your peripheral, and if you don't turn the clock on and you try to write to the peripheral, bad things will start to happen. Sometimes hard faults, sometimes bus faults, and other things that you don't want to happen. All right, we will stop here for today.